100% on the qualifier.
100%?
Yep.
I think I need to talk with the qualified committee, only allow 3 of you guys.
That would be nice.
Go ahead, I'm only the masters. They're not going to be too impressed.
If I can, I will tell you a question about thermodynamics, but I cannot, unfortunately.
So there's a thermodynamics question.
Yeah, of course.
Lord.
They ask me for questions, I already give them.
You up on Florida Huggins?
Huh?
How do you feel about it? So you're general physics, right? Like that's what your education is?
You can define that way, yes.
Is it kind of, yeah. So you feel comfortable with like polymer stuff? Is
No.
Kind of easy enough, or that's all kind of stuff?
No, I totally different.
Okay.
I know something about the chemistry point of view. I know something about the structural chemistry or like the coordinate chemistry. I'm kind of good at it, but the or inorganic chemistry I'm okay. But for polymer, no,
Okay.
it's different from my field. I know something, but not too much.
For like the thermodynamics of the mixing and stuff.
Uh-huh.
I feel like that's translatable enough. You jump right into like the thermodynamics of the mixing of they have like I took the polymer engineering course with Dr. Lim, and they have like slightly adjusted formulas that seem to be derived from the stuff we're going over.
Uh-huh.
But I was just wondering, like, I don't know, kind of put bounds on your education. How broadly, like, can you apply like these thermodynamic concepts just at the drop of a hat?
Thermodynamics is like very interesting stuff. I mean,
Yeah.
it's very different. I mean, because you know my background in physics. So thermodynamics is very different from other fields. I mean, there's a lot of the reason why thermodynamics is very complicated or very difficult to learn is that there's no, I mean, the bottom or the foundation of the thermodynamics is not very intuitive. It's not like mechanics, you know, the F equals ma, you know F, you know F, you know A. Everything more measurable. But thermodynamics, if you go to very fundamental statistics, we don't know. I thought it won't come.
Oh no, I never miss class. I try not to.
I will keep my class short, okay?
You're
Okay.
gonna keep it short?
I will try to keep this short, give you more time, okay? Today we're going to talk about phase diagram. That's it.
That's it?
Thank you for coming. Nah, it's fine. I mean, let's talk about. I will try to be brief, but still don't want to sacrifice the topic. Because I don't want people online complain. Ah, this guy. Okay, we're going to talk about phase diagrams. Okay, next chapter. Oh, by the way, midterm. Midterm we only cover until
Homework 2?
solution.
Oh, so are you gonna do another homework?
No, after that,
Okay.
after midterm. Okay, so next week, we're going to start talk something, we're going to finish the diagram, and then we're going to review what we learned. Okay, I will also tell you what's the scope of the midterm. Basically, homework 1 and 2, but slightly to the binary solution. Okay?
To the what solution?
Normal solution, ideal solution, non-ideal solution, we just
Okay.
mentioned. Okay, but from now on, we're going to talk about the phase diagram and the phase transformation. That's not covered. Okay? That's something else we're going to cover in the final exam. But again, for the final exam, we will not visit. We will not visit midterm anymore. Okay, don't bother. I mean, I don't want to make your life very complicated.
Is there a final project?
This guy always want to make his life very miserable.
No.
No project. Just the final exam, that's it. Phase diagram. Okay, so the phase diagram, what's a phase diagram? Anyway, doesn't matter, I don't know what phase diagram. There are so many different types of phase diagrams. Okay? But for this one, we just talk about the binary phase square. That means we only consider 2 elements, okay? Or two components. Okay, the first concept we're going to talk about is, we call it, and mixing is not the very terminology speaking or technically speaking, it's not very precise description, but we can still call it a mixing phase diagram. But I will, typically you do not see the terminology, but I think eventually you'll know what I'm talking about, okay? The reason I'm talking about it is very important to help you to understand how we build up the phase diagram in different kind of systems, or even more complicated systems, okay? We briefly talked about it last time, but let me introduce more properly. Remember, one thing is when we talk about the mixing two compounds or two elements, so we have this type of delta G, right? Delta GM. Okay. So this is the component A. This is component B. The X is the ratio of XB inside the entire component. Where's the undergraduate student? He doesn't have qualified evidence, right?
He's always late.
That guy's funny. Anyway, so so we're talking about if this is ideal gas or regular. I mean, not talking about regular. Okay, we talk about regular. We talk about the regular solution. Okay, so we have something like this, right? We have something like this. But one thing you gotta remember, we're talking about delta G, right? But if you read textbook or see some references, whatever, typically we do not put delta G there. We put the G. Okay, we put the G. Actually, it doesn't make too much difference. And all the conclusion we're going to show that exactly the same, but something different, okay? Something different. As I mentioned, it doesn't change the conclusion. Because, I mean, eventually the G equals to what? Equals to GA non and plus GB non plus delta G, right? GM, M means molar, okay? Or GMA, GAM, GBM, okay? It's molar. I'm sorry. Let me write it more properly. We can write it that way, so we don't need to talk about it more. We can write it that way. It's XA mu A non, okay, original plus XB mu B non plus delta GM, okay? So that means on this end, we're going to shift a little bit. Okay? This is delta G, this is G. So that means if you plot the J, if you plot G as a function of XB, it's not necessarily symmetric, okay? It can be something like this. This can be tilted. This can be tilted, okay? This can be tilted. Okay, and this point is the mu A non, and this point is mu B non. Okay, it's mu B non. Okay? But the interesting thing is the lowest point always in the center. The lowest point always in the center, okay? Because if you do the derivative, the lowest point, hold on. No, not necessary. Anyway, so it's tilted. It's tilted. But you can find that eventually when we talk about the stability of the solution or whatever, it doesn't change the conclusion at all. Okay? This is one thing I want to emphasize. Okay? The other thing is that we already mentioned. So if I have a compound, if I have a mixture or a solution with this the ratio of XB, okay, then inside this solution, the chemical potential of component A and chemical potential of component B are not their original value anymore, right? Because it's just mixed, okay? Then their chemical potential can be defined by do the tangent line of this point, and then this point is the mu A, and this point is the mu B. Okay, that's the chemical potential of component A and B in this specific solution. Okay, in this specific solution. If I change the ratio, the component also changes. I mean, the chemical potential of A and B also changes. Okay, this is what we're talking. Got my points? Okay.
Can you leave the graph on the board?
Ah,
The right graph, can you leave that on the board for a little bit?
yeah, I will redraw it.
Okay.
I will redraw it. I'm redrawing to make it larger. Okay. This one is the A component. This is the B component. Okay. And then this is the GM. Of course, this is also GM. So suppose we have solutions like this. Okay. This one then is the mu A non, and this one is the mu B non. Okay. This is the pure A chemical potential, that pure B chemical potential. If we talk about the compound, for example, at this point, okay, so we just do the tangent line, here, okay? And this one is a specific B, okay? This one is mu B, this one is mu A. Okay? And one thing, remember last time we talked about this is how we form the, and this one, at this point, the GM XB is simply equals to XA mu A plus XB mu B. Okay? At this specific point. Okay? And if, I mean before the mixing, okay, before we mix these two compounds, the chemical potential of the system actually is here, right? Correct? And at this point, is the GM non XB is simply equals to XA mu A non plus XB mu B non. Correct? And this one, from this point to this point, this is the delta GM, right? Delta GM. Correct, everybody? That's the delta GM. Right? And the delta GM equals to what? Delta GM equals to alpha XA XB plus XA RT ln AA plus XB RT ln AB. Okay? Remember, this is what we talked last time. Any questions? This basically just review what we talked about. Correct?
So, up at the top, that's before mixing. And
Yeah, that's before mixing.
that's
This
the
is after.
parabola, it's after mixing.
Yeah, that's the reason why you can mix them, right? That's the reason why you can mix them, right? Because the total Gibbs free energy lower than, right? Correct, everybody? What's your question? Oh, no. Is that clear? All right, so then.
You're so close.
Oh, yeah. Okay, so remember we're talking about the regular solution. Okay, we're not talking about the ideal solution anymore. We're talking about the regular solution. We start to think about the interaction between atoms and they can change, right? This term basically is the change of the interaction, right? As I mentioned, if the mixture A and B become more repulsive, then as the temperature going down, the curve going to evolve, right? Going to evolve. So this is the GM, okay? This is the GM. This one is the GM. Okay, this is A, this is the B, XA, XB, okay? So eventually, as the temperature going down, you know that the G is what? GM equals to HM minus TS, right? Correct, everybody? Think about if the entropy doesn't change. If the oh, hold on, I think I made a mistake here. That's really nice. Whether I'm right? Yeah, everybody. Is that right? It's right. No, it's not right. It's X. Okay. It's X. It's not A. Anyway, so this is the expression, right? Gibbs free energy equals to enthalpy minus TS, right? So you can see that S doesn't change, right? It's just a configuration entropy doesn't change. So if it's fixed, right, and the interaction is fixed, then as the temperature going down, this term, the contribution of this term becomes less and less. Correct, everybody? So if the system become more repulsive, and eventually the Gibbs free energy will go into something like this. When the temperature is low, it looks like this, right? And when the temperature is going up, and eventually it's going up, it's going something like this, right? It's going something like this. This we already mentioned last time at the end of the class. Okay. Right? Let's have the pump. Then we can see. Let me draw it even longer. I want to make this clear for everybody. Really bad at handling. Okay, this is better. Okay, looks like this. It's flip, okay? And this one because of repulsive interaction between atoms. Is that clear? Okay. Then, question comes. Originally, you know that if I have originally at the high temperature, if we have a compound here, okay, this one is Xb. Okay, we know that this one is stable, right? This one is stable, correct, everybody? But right now, if the temperature is going up, do you think this point is still stable? As the temperature going up, do you think this point is still stable? Probably not, right? Let me show you why it's not stable. Think about it. So,
Does it have anything to do with the slope?
that's what we're going to talk later. It's indeed depend on the slope. Okay? It's indeed depend on the slope. By finding the slope, we further distinguish the unstable zone into metastable area. And the other area we call it the spinodal area. Okay, that's what we're going to talk about. Okay, but so far right now we just want to analyze whether it's stable or not. Okay. Yeah, it's unstable. But why is unstable? Look at it. So if this point, so right now we have the XA. Okay, the compound is something like XB plus XA. Okay, so this is the compound we have, right? Or like the solution we have. So think about it. Then the solution becomes separated into two parts. Okay? One part goes through here, and the other part goes through here. Okay? That means the ratio deviate. Okay? This one XB prime, this one SB prime prime. The only thing we need to do is make sure that XB prime times plus XB prime prime equals to XB. Okay? We just make sure that the conservation of the atoms. That's it. But these can separate into two phases, right? They have different XB values. Okay? And then if we have this kind of mixture, you can see that the total Gibbs free energy drop down, right? That means the system prefer to stand on this point instead of this point, correct? Because the total free energy lower down, right? And the same thing, this one can keep moving down. Okay, can keep moving down. It becomes even lower, right? Then the question is, when will this kind of mixing process stop? Or what is the lowest achievable Gibbs free energy? You can see that we can keep moving down, right? We can keep moving down. Okay? We can keep find another ratio or another mixture with a lower Gibbs free energy. Okay? Originally, this is the Gibbs free energy but right now it's here. My question is, what is the lowest point we can achieve?
Kind of a straight line connecting those two local minimums, right? To
Let's
cut
see.
that hump out.
Let's see. Look at this is your local minimum. This is your local minimum, right? And then is something like it is something here. It is something here, right? Can we go even lower? Actually, we can go even lower. Actually, let me show you why. Look at this is the local minimum. This one is the local minimum. Okay? So if you join these two local minimum, it's something like this. Or we can make this one more exaggerated. So it's something like this. Okay? This is the local minimum. This is the local minimum. We just draw a straight line here. That's know the variation is not very significant. But anyway, so let me try to explain why it's like this case. Okay. Assume this is the community.
So it goes from local minimum to local minimum?
Yeah, that's from local minimum to local minimum. Actually, we can move even lower. Right? Actually, the minimum point are reached by the line that tangent to this curve and also tangent to that curve. That's the lowest point you can reach. Right? The reason is what? The reason is if you touch this local minimum, you may have another touching point. Right? That means you still have some room to move down.
Yeah.
Until this line only have one touching point with this part and only one touching point with this part. So what's the definition of the straight line has only one point touch each other? That's the tangent line, right? So that means the line which tangent to this bottom and this bottom define the lowest, gives the lowest, gives free energy. Right? That's the cotangent line, right? Is that clear to everybody? Okay, good. Okay, and then we know that eventually we have something like this. Okay. Okay. This is the line. Okay. This is the cotangent line. Tangent line. Did I correct? Tangent? Tangent. Is that correct? Spelling correct?
Yes.
Okay, that's good. All right, so then this point is the minimum Gibbs free energy we can achieve with the global ratio of XB. Okay, and then of course we have two separate components at this moment, right? Two faces at this moment, and one face is at this tangent point, and the other face is at this tangent point. You know what I'm saying? So then we know that this one probably called. And then at this point, we can call this one is alpha phase. This one we can call is beta phase. Okay? And then this one is X alpha phase, B, and this one is beta phase. Okay? And the alpha phase is not a pure, it's a dominated phase, but it's not pure A phase. Okay? And this one, the beta phase is the B element dominated phase. It's not pure B phase. That means they have more B atoms. This part have more A atoms, but both of them are still mixture. Okay. Okay. Then the question is, we know. Let me draw this one very quick. But once again, this is not phase diagram yet. Okay, but we are very close. Okay, this is A. This is the B. This is the XB. We know as the temperature changes, the curve looks like this. Okay, this is T1. This is probably T2. Okay, and then this is the T3. And then we have T4. Okay, we have T5. Something like this, okay? This is T3, T4, T5. Okay? This is because the temperature is lower and lower, okay? The T1, T2, larger T3, larger T4, larger T5. Okay, as the temperature go up and up, the minus TDS, this term become less dominant, okay? And then if the delta H is larger than 1, you know what I'm saying? Then it's more repulsive, and eventually the Gibbs free energy from this concave become convex, right? Become convex. And go back here to see that as long as your beginning, your ratio at the beginning and then locate in this range, it will decompose it into alpha phase and beta phase. Correct, everybody? But if the original point is here, it won't decompose it. Right? Although we can see that it looks very, I mean, it has a slope there, but this phase is stable. Okay, this phase is still stable. Okay? That means this area is a stable area, and this area is also stable. But something in between is unstable. Correct, everybody? Right? Okay, let's go back to here. So at the, we call this one is T. Okay, this is A, this is the B. Okay, CT1. T1 is here. T1 is this curve. Everything is stable. Right? Everything is stable here. Correct, everybody? And then let's see T2. Okay, T2, this point is something probably start to decompose it, okay, because it's flat here, right? So we can define this area here, just put it here. And T3, this is the cotangent point, these two points share the same tangent line, okay? And we go here, we go here, and this one is T3. And we know this area is unstable, correct? And we keep moving. Again, this is not minimum line, okay? This is just a cotangent point, okay? This is not minimum point, okay? They're not minimum. They are just cotangent point. We have here. We have here. Okay. This one is T4, okay? And we keep moving. For example, this is T5, and probably cotangent line somewhere here, very close to the edges. And this one is probably here, very close to the edges. Okay? This area not stable, this area not stable. And eventually, we can just connect the envelope of this point and got this area. Okay? And inside it is unstable compound, I mean the mixture unstable, and outside are stable. Outside are stable. You know what I'm saying? And this one is a typical binary solution phase diagram. Okay?
Into where the dashed lines are drawing out? I mean, so those are the tangent lines, and you're dropping them down, but what does it convert to on like the other graph? Is that a derivative? Is it a...
There's no derivative. I mean,
right.
You mean this line, right? This one, this point, and this point, just like we draw a cotangent line.
Sure.
Right? And we know this region is unstable.
Okay.
So we just project this point on this line. Okay, this is, for example, this curve is T3. The T3 axis is here, and we project this point here, and this point here. That's a tangent point.
So it's the minimums, basically.
It's not minimum, it's cotangent.
Like where the alpha and the beta is there, that's where you're drawing vertical lines on there.
They are not minimum. As I mentioned, this is just the cotangent line. If I draw, if I draw straight line, tangent to both points, this is the tangent point. This is the tangent point. But they are not necessary to be the minimum point. Okay? Because even it's a local minimum point, we can still find the total Gibbs free energy lower than that. Okay, the lowest one is defined by the, remember? I draw this one. For example, like this. This is the minimum, this is the minimum. Okay? So if you draw this minimum line, we still have some space to move the line further down. Okay, and the lowest, and you can see that this one as well. We can move it further down. The lowest, the line which has the lowest energy, Gibbs free energy defined by the tangent point instead of minimum points. Okay. Any questions? I give some time to think. Yeah.
Could you please explain again how does the T1, T2 correspond to, like, the side of the curve? Like, how do you obtain the T1, T2 lines from above?
Oh, no, I mean, this is, I mean, you understand this curve, right? I just draw a diagram. This, the y-axis is t here. So this curve is T1, I just find the corresponding T1 label here. Okay, this, and then this horizontal line corresponds to the T1 line, right? And this is T2, this is T3, right? T3 is just a straight line on this diagram because this y-axis is T3. So the T3, this is just a T3. You know what I'm saying?
How do you know that the intersection corresponds to the tangent lines?
You know, we just draw a tangent line here, and then directly project this point to this point.
Oh.
You know what I'm saying? And yeah, just straight, directly go down here, straight vertical line. Because they share the same component ratio, right? This one is probably XB, and this one is also XB, another XB value. Okay. Okay, another way. Let me tell you another way. Okay, so we know that in this range, the phase are not stable anymore, right? This range is from XB1 to XB2, okay? Two XB values, right? And then if you see from another figure, at the T1, this is the T1 line, right? And this one is XB as well. So in that means as a constant T1, as a constant T3 in this case, in this range, the phase are unstable, right? And we keep drawing. We just draw this kind of unstable region or unstable zone across all temperature ranges. And eventually you form this kind of dome shape, right? Because as temperature goes up, as the temperature going up, the Gibbs free energy actually going down, okay? Right? And all phases become stable, okay? This is high temperature, this is low temperature. But on this one, this is low temperature, this is high temperature. The temperature sequence is opposite.
I have one last question. How come the parabola at the bottom doesn't touch that T1 line? Is there?
Oh, because
rotation?
the T1 is all stable.
Okay.
I mean, this area only labels which area is unstable.
Yeah.
But for T1, everywhere is stable. So it doesn't show up. The T1 line is still there, but everything's stable.
Geometrically, the difference between T1 and T2, they're roughly the same shape, but there's just a difference in
Yeah.
Is
Yeah.
that so?
Yeah, exactly. So we do not worry too much. I mean, the phase diagram cannot tell you how much the Gibbs free energy change, but it only tells you whether it's stable or not.
Okay.
This is unstable area, so we know that there's a phase separation in this area. All other areas are stable areas. Okay, let me redraw it. So we have so many lines here, so probably got a little bit confused or it's not very clear anymore. So this is T, this is the A, this is the B. I mean, phase diagram actually looks like this. Okay, all these areas are stable solution. Okay, stable solution. Okay, and in this area, still stable, but it's more like alpha phase. Alpha phase means A dominated phase. Okay, and this one is a beta phase. Okay, and in between is a mixture. Okay, that means between we do not have the stable solution anymore. Instead, it decomposes it into two mixtures. Okay, got that point? That's corresponding to this area. Okay, again, so for example, at the beginning, if we have a alloy or like solution starting at this specific XB point, the temperature going down, everything's stable. It's just like going down, everything's stable. And then we touch this point, it starts to decompose it. And then it's entered this area, right? It starts to decompose it into this compound and this compound. Got my point? Yeah. And you can see if the X point is here, if the starting point is here, the starting point is here. It's stable, all down to probably T5 is still stable. Okay? But if you keep cooling down, probably it's have phase separation. For example, it's here, if you have starting point here, when you reach this point, it's still stable. And when the temperature cool down to this area, it decomposes it. Okay? That's how we read the phase diagram. That clear? And that's the reason for this one, for this area, we call them the miscibility gap. This area we call is the miscibility gap. Okay, miscibility gap. Miscibility means unable to mix or dissolve. Okay, miscibility gap. That means in this kind of area is a gap. Is a gap separate these two stable areas, right? And inside this gap, you cannot mix them. And outside you can. Got the point? That clear? Make sense? Okay.
So you said when temperature is going to increase, your Gibbs free energy decreases, which makes.
With the temperature going up, the temperature going up in this way. You know what I'm saying? The temperature going up, then the entropy contribution start to dominate. You want to have a higher entropy. That's the reason the stuff become to mix, right? But when the temperature going down, the entropy contribution drop down, and then you have the repulsive enthalpy. They want them separate. Basically, it's about the competition between the entropy and enthalpy. At a low temperature, enthalpy dominate. At high temperature, entropy dominate. Got any points? And have you heard about the concept right now? It's a very popular concept called the high entropy alloy. Have you heard about it? The concept is like this. So think about it. So we have Gibbs free energy. We have delta H. We have this one, right? So we know that when you cool it down, if this part is a repulsive interaction, that means the phase prefer to separate, right? At a low temperature. Okay, we have temperature going down, this term going down. The entropy always want the system as messy as possible, right? But when the temperature cools down, the entropy contribution can less, and this dominate, right? So what if I make this term really large, as messy as possible? Then even at a low temperature, this part still dominate. And then we can control or compensate for the trend of phase separation. Okay, this is the principle of the high entropy alloy. We just make the system very, 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 very messy. So even you have interaction, it doesn't separate. Okay, you know what I'm saying? That's the principle of a high entropy alloy.
Professor, is this graph for slow cooling or rapid cooling?
A good point. It's always slow cooling. It's always slow cooling. Because for each point is a thermal equilibrium. Okay? If you're fast cooling, probably you can freeze this mixture even at high temperature, even at the low temperature. Okay? You quench it. Okay? But all the phase diagram is only work for the slow cooling or like the quasi-equilibrium process. Okay? Yeah, you're right. For example, sometimes you will find that we have another phase down there. We have another phase down somewhere here. Okay? For example, this is a miscibility gap. For example, like this. Let's talk about it. So this is not. I mean, eventually we won't talk about it. Okay? So some phase diagram looks like this. Okay? So you can see that we have some. If we cool down from here, we will have phase separation to this point, right? But we don't want that. Okay, we want some have very uniform phase, solid phase here. So how can we do that? We cool it down to this point and very, very quickly go through this region, so that the atom have no time to reorganize themselves. Okay, and suddenly reach this stable place. That means everything's still stable. Okay? So that's we call it quenching. Okay, but of course, you can make phase separation by annealing it. Okay, you just warm it up and very slowly cool it down. Then just give the atoms some time to reorganize themselves. Okay. Remember, atoms don't have mass, right? It takes time for it to move from one place to the other place. Right? Although thermodynamics told you, okay, this process can happen, but it takes time. If you make the process very fast, you simply have no time to do the drop. Okay. Questions?
Professor, just one more.
Yeah, go ahead.
So, Professor, if we do this rapid cooling,
Yeah.
does this become a high entropy something?
Not necessary. Higher entropy is not defined. Yes, that's true. The entropy of the system definitely higher. Yes. But the definition of a high entropy alloy is not like this, okay? You can see that it's not proper to say that, but high entropy is a dirty alloy. Dirty alloy. Salad. Okay. So after we know this one, the question is, how can we find the T2 here? Okay, T2 is the very top of this miscibility gap. That means below T2, it's possible for us to start to observe the phase separation. Not necessarily always, because if the beginning composition is here, even below T2, we still don't have phase separation yet, right? But the question is that when will this happen? Okay, what's the highest point here? Okay, where is highest point here? So to answer that question, we still need to go back to this one. Okay, we still need to go back to this one. So we know that if the molar Gibbs energy curve and the function of xb looks like this, everywhere is stable. Everywhere is stable. Correct, everybody? And then that means the entire curve are concave, right? So if the curve some part become convex, then it's become unstable, right? The region between this cotangent point are unstable. Okay, this region is unstable. So in that case, we just need to find. We know that this curve evolved from this shape to this shape as a function of temperature gradually. We just need to find the temperature point at which the curve transform from the convex to concave. Right? Basically, we need to find what's the point that the curve change from the concave to convex. What's the name of it? It's called the inter.
That's what the second derivative is 0, right?
Yeah, but what's the name of it?
Concave?
It's called the interflexion, right? Inflection
Point of inflection.
Huh?
Point of inflection.
Yeah, inflection point, right? We need to find whether this curve has some inflection point. So basically, yeah, you're right. So basically, we just need to find somewhere. Give this, right? You can see that for this curve, everywhere we cannot find this point in anywhere, right? But for this point, for the entire curve, we can only find one point, right? Give the second order derivative. That is the critical temperature, right? But for this curve, we can find 2 points, right? You can see 1 point here, 1 point here, right? We can find 2 points. And we are looking for a curve that only has 1 point. You can see that, eventually something like this, right? So we have another point here. So then, since we know the mathematical principle of it, we can just do the calculation. So in order to calculate, we still need to know, we know that the GM equals to what? Equals to XA, mu A non plus XB, mu B non plus what? Alpha XA, XB. Hold on. Can I erase this one? Yeah, let me erase it because I want more space to write down the entire equation. By the way, so what's the number of this class? It's 5106. Who is teaching 5104?
Fang.
Huh?
Dr. Fang.
Dr. Fang.
You think?
Or the associate chair of the department.
Yeah.
There's one student sent a message saying that there's something wrong. But send to my email. I'm not teaching that class.
What's the title of that class?
Intermediate
expression. So basically, we are only calculating. We are calculating the critical point. Critical point, critical temperature of regular solution. Okay. We'll calculate the critical point, critical temperature. This is the critical temperature, okay, of a regular solution. Okay, because we can write down that we can strictly write down the Gibbs free energy of the regular solution, but for the ideal solution, there's no phase separation for sure because we don't have the interaction. It's always stay in the mixture shape. Okay, and only for non-ideal solution, we may have the unmixing. Okay? And for the non-ideal solution, we can only write down the order of the regular solution. That's the reason we just use the regular solution to do calculation. Okay. And this one equals to what? Minus xb. Okay. Basically, you know that all the xa simply equals to 1 minus xb. Okay. So xa and xb are not independent. Okay, they are independent. They are dependent on each other. So the dgm exb then equals to minus E naught plus mu B naught minus alpha this term is what? Okay. And plus minus RT log X A or no 1 minus XB. Okay. And plus 1 minus XB and RT is ln is the XB. Let me see. This is XB minus 1 plus RT ln XB plus RT. Okay. Is this correct, everybody? I think I probably made some mistake. Anyway, is that right? Did I make it correct? May or may not. Hold on, let's see. Tracking on my notes, I made some mistake. Okay, anyway. Something wrong here?
I trust you.
Huh?
I trust you.
I don't trust myself. Okay, anyway, let's keep moving. So if it's wrong, we can figure it out, okay? Let me do it. So this, I mean, the only thing is that probably this part. I just skip several steps. right? So we do the derivative. We do the derivative, and this one is what? This one, I probably something wrong. This one is equals to RT log 1 minus XB times minus XB. Now, so we do the first order derivative, and then this one becomes negative RT log 1 minus XB. And then we have another term plus 1 minus XB, and then RT. We do that one is 1 minus XB, and then we have a negative sign here. Okay, this one is here. Should be right. Yeah, should be right. Okay. Then we see this term. This term is what? This term is a negative RT, right? Correct, everybody? And then these two terms just cancel each other. So we have mu B non minus mu A non, and plus alpha minus 2 alpha XB, and minus this one we should be able to remove something. No. So minus RT ln 1 minus XB, and then plus RT ln XB. Right? This term and this term cancel each other. Correct? Right? And then we need to do the second order derivative. This term doesn't work, doesn't exist anymore. This one just equals to 2 alpha. And this one minus. Why I'm doing this to myself? I just kidding myself. Supposed to be positive side plus RT. And then this one should equal to 0, right? This one should equal to 0.
Then you solve the t.
Huh?
Then you solve the t.
Then we solve the t, right? This one equals to 0. Okay, so we know that I think there's the solution, right? Okay, so we know that if this is the regular solution, then the A component and B component, they are symmetric to each other. Remember, they're symmetric. All the expressions here are symmetric, right? We can replace A and B, doesn't matter, right? Consider the expression A and B are symmetric, right? So the argument is this kind of the inflection point should be in the middle. Right, everybody should be in the middle of the curve. Right, that means at the very top, that means you can see that in the phase diagram, the top of the dome should be exactly in the center. Okay, that is for the symmetric. Okay, but I'm not talking about the real solution. I'm talking about the regular solution. Okay, they are symmetric to each other. So the XB should be equal to 0.5, right? At the very top, right? Only for the regular solution. Then if XB equals to 0.5, okay, for regular solution, then what we have is minus 2 alpha plus RT. That is half plus RT. That is half. Should equal to 0, right? Is that right? Let's do something interesting. Okay. Then this is 2RT. Then we have the minus 2 alpha plus 4RT equal to 0. Right? And then we have, let me see whether it's right or not. Yes. We have T equals to alpha divided by 2R. Okay? And the dt is the critical temperature. Okay?
And what is the critical temperature?
The critical temperature is at which temperature the inflection point first show up on the curve. That means on the curve we only have one
Oh, so like
inflection.
that temperature you could be just on the border of like unstable.
Yeah, yeah, exactly. The very top.
And a regular solution versus, so a regular solution is like an ideal.
It's not ideal, but the regular solution means we can calculate the only contribution to the entropy is the configuration entropy. We don't need to consider other contributions. Basically, the difference between regular solution and the ideal solution is we need to think about the interaction variation between atoms. Okay, but the entropy contributions still come from the configuration. That means the random distribution. Okay. Okay, so let's give you some qualitative expression of explanation of this term. Okay. Where's the eraser?
Your eraser's at your foot.
Yes.
So Professor, these lectures will also be in the midterm, right?
No. No. But we'll be on the final. Okay. So let's briefly talk about that one. Okay? We call the TCR equals to. That is a critical temperature. That means at which temperature we will start to observe, we are possibly start to see the decomposition or mixing. Above this temperature, no matter how you mix the two elements, they will not mix. Okay, everything's stable. But below that one, certain area, a certain ratio, a certain value of the XB will lead to the mixing of the solution. Color points? So see the phase diagram? Okay, this point, this is the TCR, okay, critical temperature. That means above it, everywhere is stable. And below that, the miscibility gas start to show up, okay? What's the reason for that? Remember what's the definition of the alpha? Alpha is a z, that is a coordinate number, the F-Gallup constant times the EAB minus half EAA plus EAB, EBB. Correct? That is the expression of alpha, okay? And think about it. So first, at the beginning, for example, we have AA interaction. This is energy level of the AA interaction. This is the BB interaction here, okay? This one is just the central mass of these two interactions, right? Okay, this is the central mass, correct, everybody? So if the interaction more repulsive, that means the EBB is here, right? EAB is here, correct, everybody? So basically, we have a barrier here, okay? If it fall to this area, it becomes stable, right? We have a gap. We have not gap. We have a energy difference. That's a delta E, right? This is repulsive. Okay, make the system prefer to go back to this state. Okay, go back to this state. But if we have the thermal energy or the entropy to compensate for this barrier, then the system is stable. Okay. So what is typical thermal energy? Thermal energy typically is the N. The thermal excitation is in this range, right? This K times T basically is the energy induced by the temperature or thermal fluctuation, correct, everybody? K is the Boltzmann constant, T is the temperature, right? So then this one is roughly, not roughly. So if the thermal excitation is briefly or in the same order of this delta E, the system is stable, correct, everybody? If you lower that one, the system becomes it, correct? And you can see the delta is what? For each of the atom, then the delta is just right? Is a Z. For each of the atom, for each of the atom. So we do not have the F-Gallup constant anymore. So that is the EAB minus or okay, correct? But we need to consider how many bonds there, right? We need to break all bonds before we can release data, right? right? That's the reason we have Z. And of course, you just have the outcome constant, and you times the other outcome constant on this end, then this one become R, right? This RT is in the same range, should be in the same range of the alpha, okay? And in our expression, we just have R, have 2 here, right? Have 2 here. That's the only factor reason. So you can see right now they are roughly the same level, okay? Got the points? So that means the thermal energy help us to compensate for the trend or the energy to decompensate the system, right? Because if the system decompensates, release energy going down, right? But we need to inject some thermal energy to make the system excited to this point, to stabilize it. And then the KT must be roughly in the same range of delta E. Okay, then we give this expression. Okay. Got points? So you can see that we have 2 factors, depending on which factor dominate. The dominant one will win, right? So temperature high, the system can jump from this point to this point, right? Then it's stable. When temperature low, it's go back, you decompensate. Okay? Okay, so lots of things. Okay. I promise I'm going to finish in 15 minutes. Okay, the second concept we're going to talk about today is we talk about the miscibility gap and mixing, right? We talk about something about metastable state and spinodal decomposition. Spinodal decomposition. I did not follow the sequence on the textbook because I don't think it's the proper way for us to introduce the concept. So I just flip the chapter sequence. Okay? And in the textbook, it doesn't introduce the spinodal either. But I think if I immediately introduce the spinodal decomposition, it's more organic. Okay? Because we already mentioned all the key concepts. Okay? All right, so let's still look at this one. Let me draw it larger. Make it larger, okay? Just want to make it very large. This is G, A, B. Okay. We mentioned that this is a cotangent line. My drawing is improving, right? This is cotangent line, this is cotangent line. And in between, this is the miscibility gap, right? This is the miscibility gap. That means in this region, the compound or the mixture are not stable, right? The solution not stable. It's separate. Correct? That's what it's saying. Right? Look at it. If we have at the beginning, if we have something here, okay, the ratio is here. So if at the beginning xb is here, correct everybody? Then we have the phase separation, okay, decomposition or whatever. So at the beginning, but you know that it won't jump down to this point immediately, right? It have to separate gradually, right? So at the beginning, we may need to separate into these two phases, okay? And they can see this line gradually move down to this line, and we finish the separation, right? But at the beginning, we need to separate to these two, correct everybody? And you can see that at this point, this is the chemical potential, right? This is the, not chemical potential, this is the Gibbs spray energy, right? And you can see that as the line moving down, the chemical potential, the Gibbs spray energy keep blowing down, correct everybody? That means this process can happen spontaneously, correct? Right? That means as long as starting points here, it will decay or it will decompose and mix spontaneously. Okay? Then let us see another possibility. Okay? It's here. It's still the same chart. Okay? We know that this one is unstable region. Here is unstable. What about here? We know this point has higher Gibbs free energy than this point. So we suppose this mixture will separate into these two mixtures and lower the Gibbs free energy to this point. Correct, everybody? Right? But let's see what's going on. So when it starts to decompose, to separate, it separates to this point and separates to this point at the beginning, okay? And you can find that these 2 points, the line, the connection between these 2 points actually is higher. Correct? Right? That means for this one, the Gibbs free energy just drop down. But for this one, if we want to reach this point, the Gibbs free energy first go up and go down. Correct? Then we have the barrier here. The system needs to go through the barrier. Right? But this one, this is no barrier. Then this area is spontaneous decomposition, this one is not. Okay? That means if it doesn't go through the barrier, it prefers to stay this point instead of this point. Right? Then this position we call it the metastable state. Okay? That means the decomposition or phase separation not necessarily happens spontaneously. Okay? Although the Gibbs energy is not preferred, but before it's reaching to lower Gibbs free energy, the total free energy needs to go higher. Okay? Got my points? So what's the difference between these two scenarios? The same thing. See the curve? This part is convex. This part is concave. Right? This is concave, this is convex. Right? So how to separate these two scenarios? We need to find the inflection point on the curve, right? This is inflection point, this is inflection point, okay? That means the region between these two inflection points are unstable at all. They can spontaneously decay, right? But outside and between and inside these two cotangent lines, these are metastable states. Correct, everybody? This area metastable. This is unstable. This is the miscibility gap. Okay? And eventually, when you draw the phase diagram, besides the miscibility gap, and inside it, we have another zone. Again, at a given temperature, okay, at a given temperature, for example, T1. This is the one cotangent point. This is the second cotangent point of that curve, right? And this one is the first, inflection point. This one is the second inflection point, okay? And at the critical temperature, you know that this is the inflection point, as we just showed, right? This is very top, right? So that means these two curves always overlap at the highest point, at the peak. Correct, everybody? And this curve, we call it the spinodal curve. Okay? And this one, we can call it whatever, miscibility gap or whatever. Okay? And this area, the metastable state. And this one is a spinodal. Okay? Not spinodal. It has some consequences. Okay? If the decomposition happens in the metastable states, typically we need to overcome the barrier. Okay? Overcome the barrier. That means we need to introduce something to the system. Typically, we need to have we call it the nucleoside. Okay? For example, we are talking about the ultra cold water or ultra hot water, right? If you do not put something to disturb it, it doesn't boil. The super hot water, right? You need to put something, right? To put something inside, to lower the barrier, Okay, that one we call the nucleoside. Okay, we have the barrier here, right? So to make the process happen, we need to lower the barrier. Okay, how you lower the barrier? You just put something into it to disturb it, and you lower the barrier. Okay, and then that process we call the nucleation process. Okay, But for in this kind of the spinodal curve, we do not need that one because there's no barrier, okay? And we indeed observe this phenomena in the materials, and this is the first time I'm going to use the projector. Projector. Can you see that? Okay. See this figure? The left one? This one. This one is the aluminum germanium alloy. When you cool it down, let me draw it here. When you cool it down, you can see that we have very sharp crystals. So you can see the crystals, right? This crystal just grow, along or around the nucleoside. Okay, the small crystal just like the stick you stir the boiling water, and the crystal start to grow around it. And this one, you can see on the right hand side is the spinodal decomposition. We do not need to have the nuclear. That's the reason you can see you have really beautiful pattern, okay? Because this kind of decomposition doesn't need nuclear site. The nuclear site just randomly distributed. Okay, that's the reason the pattern is so random. But for the spinodal decomposition, it happens spontaneously across the entire material, spontaneously and simultaneously. That's the reason you have this beautiful pattern. Okay, why you have this pattern? The reason is, after you have the decomposition, different area have different kind of mechanical strain. The Young's modulus is different, right? So they modulate the Young's modulus, and then you have this kind of wave structure. Okay, but you can see that they do not have very sharp crystal structure anymore. Okay. Okay, so basically that's what we're going to talk about today. And here we go. Here's another very beautiful figure. Okay, to tell you. Okay, and in the middle is the spinodal decomposition. Okay, you don't have this clear crystal or nuclear site anymore, but on both ends you have this kind of crystal sites. All right, so good luck with your qualifying exam. I want to know who is the lucky guy. And at the beginning of next class, probably I want somebody to explain to me why this process called spinodal. What's the original word? What's the meaning of it?
The midterm, right? We won't have classes that week, but it'll be just like the homework we write on paper and submit it.
Yeah, you can.
Right.
yeah.
Okay.
For the midterm, the same thing. You can write down paper and send it.
Alright.
It says it's from the austenite to martensite, and it's from like a cubic structure to a tetrahedron, right? ECT. So this does not look like a cubic structure. However, this does.
Yeah.
This does look like a cubic structure.
Do you guys think my teaching is above average?
Yes.
Yes.
Okay.
Teacher, yeah.
And
Thank you so much. Put in my comments on the evaluation.
so I say
It's above average.
instead of this as the lattice parameter, I just set like a gamma over 2 is the lattice parameter. So right now the distance within this cube, like if I say this is the origin, so the furthest iron atom is this one.
Yeah.
So I draw a vector here and measure, calculate the length of that vector.
Yeah, that's why I was confused. It doesn't look like, it's space centered. All the ones should be the same pretty much.
Yeah.
But I think in your
But it just has these two, and this is really
Well, I
long.
tell you why. What's the physical reason for that?
So I am
I
not
did
sure.
like side
But I still don't understand why
the,
people call this. I'm just talking about the
the
original
lattice
meaning of this
parameter,
word.
and
I'm
I
not
just
talking about
went to
physics.
side
But
length.
I don't know why it's called the spinodal.
And I ended up
Why
getting
don't
this
call
for
spontaneous?
X and Y, but
It's
for
not
Z,
called
because it looks so weird, even though it says face centered, I just went with a normal
I don't,
one.
I don't know how
And
to say
then,
English word.
So you
I
said
did
this
that.
is A gamma instead of A gamma over square root 2. The
yeah, I
Z.
said this was just A gamma, but
Oh, yeah, that makes sense.
But I don't know whether to go off of that or the weird picture, you know?
Yeah.
But that was pretty much it.
But we are just extending this vector to here and like calculate the difference in the magnitude of the vectors, right?
Yeah,
Yeah,
that's what I found on the internet at least.
Uh-huh.
Let's see, the other ones were fine. This one right here, I calculated B so many different times and I kept on getting a different answer for the creep rate.
I don't remember the formula. Let me check.
I didn't ask any of the professors for help, I just,
Is this the only test you have been practicing?
this one and the other one.
The 22?
Yeah, and then besides that, just kind of in-class examples, and I read a little bit of the book, but I'll be honest, I kind of crammed it, so. I mean,
Do you want the 22?
oh, there's a 22 one?
Yeah.
Sure, I'll take it.
Yeah. This is the formula I found for a creep rate. This guy. Although I don't remember which variable corresponds to what. You said you get different answers each time you calculate?
Yeah, I ended up just doing a ratio for it because that's what I had to do for the other ones because the stress was the same and the temperature was the same for those.
Okay. I guess we have the same formula. Except is there a minus sign here?
My B is right here, but I meant to put a minus sign here, but I did a.
Otherwise, as t goes to 0, it blows up.
Yeah, I mean, it didn't matter because I just canceled them anyway.
Yeah, I am not really sure about this guy.
Yeah,
I don't remember what I was doing. I was just taking advice from GPT, and I need to revise this. I did this like a week ago.
Yeah, I mean, I don't like this one. I mean, what I kind of did, and I don't think I can do it, but just like how I ratioed, you know, 2 of them off to get in and 2 of them off to get the activation energy, I just ratioed.
Yeah, we get same Q activation.
It's just this one, like this one is just kind of, I don't know, flawed in my opinion. Because the way we solved for everything else, you think you would have to do it for this one as well, but if you solve with every single different case, you're going to get a different creep rate. But even with the same activation energy and the same whatever the n number is, the factor.
This is 3,600.
I guess this isn't like a linear relationship, so I couldn't do it, but
I converted it into seconds, which is unnecessary.
I guess I didn't think I could do, yeah, the seconds thing. I didn't think of that, but.
I'll have to go over it carefully again.
I mean, worst case scenario, I don't think they would ask that again.
But they will definitely ask something similar.
probably to do with the formula. But that one definitely confused me. But whatever, I mean, if it's like close enough, you'll probably get like partial credit for it. This one right here, for number 6.
I have hell no idea.
Yeah, I didn't have any.
I don't think the book says anything
No,
related to like an angle.
it didn't. I saw something on the internet to where, why is it